All right, hey everyone. So today we're going to go over the first half of the Unit 3 notes, ions and ionic chemical formulas. I'm going to do this kind of in parts here. So, excuse me. Today we're going to hit the concept of cations and anions for monatomic ions. So, kind of setting our base again, if you recall, an ion is an atom that has gained or lost electrons, which in turn gives it a charge. Okay, if it loses electrons, it's going to be positively charged. So if you remember in the in-class lecture, I said I used the cation is positive, right? So to remember that, losing electrons, positively charged ion. An anion then is the opposite. An anion gains electrons and is a negatively charged ion. Okay. Now, there are two other generic categories for ions. There's monatomic and polyatomic. Monatomic, the prefix mono referring to one. So monatomic is an ion created from only one type of atom or element. Okay, we'll hit polyatomic tomorrow, right? So monatomic ions are ions created from only one type of atom. All right. So down here, we're going to do some examples of the monatomic ions. So a monatomic cation is a positively charged ion made of only one type of atom. Okay, so it's a combination of monatomic and cation. So examples of this would be like Na plus 1, 1 plus, aluminum Al3 plus, calcium. So there's a bunch of them. Okay. Yes. A monatomic anion is a negatively charged ion made of only one type of atom. So a combination of monatomic and anion. So examples of these would be stuff like O2 negative oxygen, nitrogen, -3 or 3 negative, chlorine, 1 negative or -1. By the way, sometimes you'll see both the positive one and the negative one without the one on it, just with the like the plus or the negative symbol. If you ever see an ion with a charge, it's a positive or a negative, and there's no number by it, that just means it's one. Okay. All right. Now, we can use our periodic table to find most of these. All right. After yesterday, hopefully, you guys, after going through the work and stuff, that you guys figured out across the top that your charges for the columns, for the families, should look something like this. In 1A, it would be +1. 2A would be +2. Okay, and then it skips over to 3A. 3A +3. There's nothing for 4. I mentioned that. And then when you get to 5A, it's going to want to gain 3 electrons. So that's actually going to be a -3 or 3 negative. Oxygen column family is -2. The fluorine, those are also called the halogens, are 1. And then our noble gases don't really react with anything, so that's 0. They don't usually form any kind of charges, any ions. Okay, so let me zoom out a little bit here. You should have those across the top of your periodic table to help you out. Okay. All right. Now, I'm going to flip this over now. Go to the back. Okay, ionic chemical formula creation. This is actually making the formula, making a compound from the ions. All right, all ionic formulas must have a cation, a positive, and an anion. The cation always goes first. Okay. The compound must be electrically neutral. The total positives must equal the total negatives. This is balancing out the most compounds themselves. The compound do not they don't have charges. They're electrically neutral, and this is because overall the total number of positives equals the total negatives from the ions. Okay, so I'm gonna pause here for a second. Okay, so I wanted to sort of draw out this idea that a compound needs to be electrically neutral. So, excuse me. So let's take something that we already know, like water. So we know water is H2O, obviously, which means H2O, the subscripts are the number of atoms of each thing. So this means we have um, 2 hydrogen and 1 oxygen atom, right? Okay. So if we were to look at this and we use our periodic table, we would see that each hydrogen should be a +1 charge, right? So the essentially you can almost think of it like like an equation where to figure out the overall charge on the whole compound, you take the charge, take the charge times the number of atoms and you do this, and then so you get the total for that element. Okay, and then you repeat for each element. Then you add charges for all the elements. And this should equal 0. should equal 0. Now, that might seem kind of complicated, but it's really not too bad. So let me show you. Well, this is actually kind of a bad example because water is a compound, or is a covalent, but for a weird reason, it actually works with water. So I'll show that on here. Okay, so hydrogen, the charge on hydrogen, if we look on our periodic table, is a +1, right? So for hydrogen, the charge is a +1 times however many hydrogen atoms we have. We have 2. Okay, so that gives us a total of +2. Okay, our oxygen, is a -2 charge. So oxygen, -2 charge. We only have one of them. So -2 times 1, -2. Add them all together, you get 0, which is what you want for a compound. Okay, now, let me walk you through this sort of conceptually, okay? So let's take, let's see. Why don't we do aluminum So this is actually going to be aluminum and sulfur. Okay, so if we look aluminum up on our periodic table, aluminum is here. That means one aluminum ion will have a +3. So I guess I should put ion here. Aluminum ion and sulfur ion. Okay, so one aluminum ion is a +3. Okay. One sulfur ion, if we look on our periodic table, is a -2. So the question becomes, how many of each of these do we have to combine to get a 0 charge if we're putting these together? Okay, so if we look, our aluminum is higher than our sulfur, right? So let's add another sulfur to try to bring it up to that. So we add another sulfur. Each sulfur is a -2. So what's our total charge now for sulfur? Well, 2 at -2 is a -4. Aluminum is only a +3. It hasn't balanced yet. Okay, so we're going to go over to aluminum, and I'm going to add in aluminum. Aluminum is a +3. Okay, now with that, we've got a total of +6 over here for our positives for aluminum, right? Well, our sulfur is only at -2, so we're going to add another sulfur to try to balance. Okay. Now, if we total up at this point, these together are giving us a total of -6, right? And if we look at our aluminum total, +6, which means they're neutral. So what would the compound be for the combination of aluminum and sulfur? Well, you would have Al for aluminum. There are 2 of them, subscript 2, sulfur S, and there are 3 of them. So the compound the ionic compound that would form between aluminum and sulfur is Al2S3. Now, that's the concept behind how ionic compounds form. Now, here's the nice thing is you don't have to think through this concept every single time. There's a sort of a trick method that we use to help us figure out the ratio of each of these to each other that's much faster. Okay, and that's called the crisscross method. So we use, and says this in our notes, we use the crisscross method to determine the ratio of atoms needed to create the chemical formula. So if for this, okay, if I was doing the crisscross method, what I do is I take my ions with their charge. So aluminum +3 and my sulfur, let me move that up a little, and my sulfur -2. Then what we do is we cross the charges down and turn them into numbers of atoms. Okay. Now it's important to note. Well, let me do it first, and then I'll explain. So you cross down, so it becomes Al two subscript 2 S3. Okay. Now, it's very important for you to understand that this is just I don't know if I want to call it a trick, but it's a method. It's a method of figuring out the ratio. So when the numbers are up here, they represent charges on each individual ion. When you cross them down and you're making the formula, when you have the formula put together like this, they are no longer charges. The numbers in the subscripts are numbers of atoms. So when they're down here, there's no pluses or minuses. They're not charges. This means you have 2 aluminum and 3 sulfur. Okay, they're number of atoms. So it's super important for you to understand the difference. Okay. Let's go back to the notes. Swap this out. Okay, in the notes, we have this. All right. So with the ion, okay, we've got the 2 ions here. We are doing the crisscross method. So let me zoom in a little bit here. Li +1, sulfur is a -2 or 2 negative. We cross down. Okay, so we get Li 2s. Okay? If it's a 1, you don't have to write it. Similar in algebra to how if you have like 1x, like the variable x, you have 1x, you don't have to write 1x, you just write x and it's understood that it's a 1. Okay, so LIS. That would be your answer. Okay. If they give you the names like this, okay, so sodium, the cation, sodium, you look up sodium, sodium's on here, is a +1. So you'd write Na, oh, shoot, sorry, wrong spot. Na +1. Chlorine is a -1. So Cl, -1. And you cross down. And we get NaCl. Let's take a look at number 4 here, calcium and phosphorus. So calcium, Ca, again, off the periodic table, I find out that calcium is a +2, 2+. Phosphorus is P, 3 negative. Okay. You have to check these and make sure that they can't reduce. If they can reduce, you reduce them, like dividing by the same, by a common factor. Okay, so we cross down. We end up with Ca3P2. Okay. All right, let's take a look at number 5. So I skipped number 2 on purpose. That'll be on tomorrow's. Okay. So let's take a look at number 5. This is the actual formula name, magnesium oxide. They changed the ending of our monatomic anions to IDE. So oxide comes from oxygen. All right. So same thing, magnesium, look up on the periodic table, +2. Your first thing should always be positive for these, and your second one should always be negative. Oxide, as I said, comes from oxygen, which is a -2. Okay, so now check your charges to see if they can be reduced. Here they can. They're both 2's. They can be divided by 2. So we divide them both by 2, reduce them. We get +1, -1. We cross that down, and we end up with MgO. All right. So I'm going to pause for another second here. Okay. So in some of the classes, people were asking, we put the charges up here and we were talking about how in each row, or not row, I'm sorry, in each column, these are the charges for the things that are in those columns, okay? And then some people were asking, like, well, what about the B's in the middle and stuff? Like, does that go by the names? And I said, no, it doesn't. We'll worry about that later. Well, later is now. So here's the deal. The what are called something like the intertransition metals, these transition metals and some of the intertransition metals, they sometimes can form more than one ion. In other words, they can gain or lose different numbers of electrons. So they don't always have the same charge. It all depends on how they bond. All right. So we can't just know, like, say, like this whole column is a, plus whatever, something like that. So there's a little trick in the name that tells you what the charge of the cation is. Okay, and that is some of the transition metals have a Roman numeral which tells the charge on the cation, the positive charge. And the reason they have that is because if we look at our periodic table, we don't know what the charge is, but we need the charge to be able to do our crisscrossing and figure out our ratio. Okay, so for example, number 6 here, copper, and that's a Roman numeral 3, bromide. If we look up copper on our periodic table, it's here in the middle. We don't know what the charge is. So if we're trying to do our crisscross and we do, copper, Cu, we don't have the charge. Bromide is from bromine. We look up bromine. Bromine we know is a -1. Okay, so it'd be Br -1. Well, we need the charge on copper to finish this. So, but if we look on our periodic table, it's not there. That's what the Roman numeral 3 tells us. This tells us the positive charge on the cation. Okay, so the 3, so it's a +3. Now we can do our crisscross. No reduction, so we cross down. We end up with Cu Br3. Okay, so the Roman numeral is telling you the positive charge because we can't find it on the periodic table. All right, now there's a few things on here that I need you guys to add to your periodic table. I'll go over this in class as well at some point, make sure that everybody has them, but in order to do some of the stuff that you're going to do on the homework, you'll need to know this. So there are some of these in the middle that only form one ion, they only gain or lose one certain amount of electrons. Okay, so those don't need Roman numerals to tell us the charge because they only do one thing. Okay, but the only way you're going to know that is if we mark them. So on your periodic tables, I'm going to put this up here, and you guys should mark these ones that I have charges marked. So the lanthanum isn't super important, but the ones that are up here definitely. So scandium a +3, yttrium a +3, zirconium a +4, hafnium a +4, tantalum a +5, technetium +7. Then we jump over to silver as a +1, cadmium is a +2, and zinc is a +2, and germanium is a +4. Okay, that's all the ones that you need to mark. So if one of those pops up as one of your cations, then you can just go to your periodic table and find the charge because it won't give you a Roman numeral sometimes. Now, we also have some exceptions over here. See these 5 that I marked with X's? Those are metals, so they'll make positive cations. However, they don't go by the column numbers. Okay, so these 5, tin, thallium, lead, bismuth, and polonium, they will form, they're metals, they'll form positive ions, cations. But we don't know the charge because they can have more than one charge. So if you are given one of these 5, you will also be given a Roman numeral. That will tell you what the positive charge on those elements would be if you're making the formula. Okay. All right. If you stuck with me this far, I hope, congratulations. I'm going to cut this video now, and I am going to make a second video that walks through some of the problems from the homework, just to make sure that we kind of know what we're doing and that we have it down. Okay. As always, please, if you guys have questions, text me, send a message, whatever. All right. Sounds good, and good luck.